important thing is that we're using the wind speed that the turbines are going to see compared to the sound level happening at the ground. Because there's and the wind speed at ground level may well have been extremely low or non-existent a lot of the time, but it's what's happening up above that we're basing this on. All right, so then if we take the wind and the sound data and we plot it as a function of wind speed, then we get this big shotgun of points here. But the general trend is, as the wind speed goes up, the sound level goes up. Now, we've done this at many other projects, and there's normally a tighter grouping where they follow this mean line much more closely. But it is what it is. This is what was measured here. So, for design purposes, we say that when the wind's blowing at 6 meters per second, we say, well, the sound level is about 37. And that's the level that we use to calculate the 6th increase. Now the question might be, oh, why don't you draw the line way down here at the bottom of all these points? And that's because all these points are the L90 sounds are already the near minimum sound level. The normal level, the average level, you walk outside and turn the meter on, would be way up in here. These points are already representing the quiet lulls between any kind of sporadic event or anything like that. So we think it's reasonable to use the mean. And this is likely to be higher as well.
Do you have a suggestion as to why this is such a widespread?
It's because other things must have happened that were unrelated to the wind, like tractor, anything could have happened. But in environments where there's no man-made noise of any kind, then you'll get a tight grouping. But the points that don't, that are these outline points are related to something else happened that had no relation to the wind. And that's, it's in the real world, that's what happens. It never gets a whole lot tighter. But usually we see this pattern a little more clearly here. Now we did a summer survey as well. Now, there's no relation to wind here, because during that survey there was nothing but cicadas and insects going on, and they're not dependent on the wind speed. So the points just occur wherever. Doesn't matter what the wind was doing. The points are just everywhere. It's here it's 50 and it's 0. So for design purposes, we just screwed this up. This just shows that it can get louder during the summer. That's all you can conclude from this. But for design purposes, we just go back to the wind data. So here's a summary of both the surveys. So here, the summer average sound level when the low wind speed is about 45, and the summer L90 is 42, real high. And then in the winter, the average level at this low wind speed is 35. And then here's the L90, this green. These are the levels that we're using for design purposes. Just ignoring all these other higher levels. And we're just going to use the L90 in the winter as to define the background. Okay, now this one's a little complicated. So here we have the L90 sound levels that we measured in the wintertime as a function of wind speed. And 37 was the mean at 6, 39 at 7, and so on. And what we're looking for design purposes is what's the worst case wind speed? When is the project going to be the most audible relative to the background level? If we could just put in the maximum turbine level, which in this case occurs at 7 meters per second, and base the design on this 39, but what we find is that the critical wind speed is typically lower than the maximum point where the turbine reaches its maximum sound power level. In this case, this turbine almost has a constant sound power level. There's hardly any variation. All these would basically round off to 102, so there's very little change here. But here, at this 6 condition, the differential is maximum. It's where this is low, this is at the lowest, and this is at the highest. And it's a 65 differential between these two. At the next wind speed, the background's going up, and the turbine's going up just a little bit, but the differential's going down, dropping, dropping, dropping. Because at very high wind speeds, the background level goes up indefinitely. You know, when a hurricane comes, people say it sounds like a freight train. There's no limit to how loud the background can get. The turbine sound level, it goes up, usually peaks around 7, and then stays the same, up all the way till cutout. It never increases. It's that once the rotor gets going at its full RPM, the noise just stays the same. At very high wind speeds, the background just is very much louder than the turbines. So we, for modeling purposes and design assessment purposes, we're focusing on the 6 meter per second wind condition. Okay, so the background level at that wind speed, 37. And we assume that this 6 increase is cumulative. And we're not just going to add 6 to 37 to get to 43. We're going to assume that it's cumulative, that the background and the project level are going to add up to both create this 6 increase. Now this is a little complicated, but what that means is we say when the project level gets to 42, and we add that to 37, that's going to equal 43. Now, decibels, they add up logarithmically, so it's not 37 plus 42 equals 79. It equals 43. So it's a conservative, a slightly conservative way of looking at it.
Why don't you take a minute and go back through this thing again?
Yeah. This is a perennially confusing point. We estimate that the background is 37 under these critical conditions, when it's the worst case conditions. We then say that the project can be 5, if the project is 5 over this, that is going to lead to a total 6 increase in the overall sound. So we're not adding 6, we're saying a 5 over the background is where the DEC threshold exists. Okay. All right, so we have this 42. That's the point where the project would cause the background level to go up by 6. So then we do a sound contour map of the project. And we base the calculations on this ISO standard, which